Hello everyone. Today we're going to talk about optics. What are optics? It's just the study of how light behaves. And we look at these different items like prisms and mirrors and lenses and how they affect the way light travels. So you're at the Pink Floyd concert and you see all these pretty lights and you're wondering, how do they make these pretty lights? Well, it's because different colors have different wavelengths. You can kind of see that right up in here. And when this white light goes through this prism, because they have different wavelengths, they refract differently through the prism. And that allows us to see all those pretty colors. And here's some stuff that you guys already know. You know about the incident ray, the reflected ray, and the law of reflection. And you also know about the normal. But you also know that the angle of incidence, this angle right here, is equal to the angle of reflection. So when you're driving your car and you're looking in the rearview mirror, when you see your kid sibling in the back seat kind of talking back to you and doing those funky faces like, I don't have to listen to anything you say. Well, little do they know, because you're looking in the mirror, you can see them just as easily as they can see you. That's that law of reflection. And when that truck in front of you has that sign that says, I can't see you if you can't see my mirrors, a law of reflection. So the angle in is equal to the angle out. And those angles are between the ray and the normal. But those are things that you probably already know. What we want to talk about today is about mirrors and maybe some lenses that are not flat. So the first type of mirror that we're going to talk about is a convex mirror. So you see the diagram, and you can see that the mirror curves inward towards you. And you can also see what it does to the light rays and how when the light rays come in, they reflect and they go in many different directions. They diverge away from each other. The most common places you'll see these kind of mirrors used is possibly in a convenience store or in a bank, or maybe on the side of your car where the side view mirror is. One of the things that they do is they always increase the viewing angle. But by doing that, that makes the image appear smaller than it actually is. And it produces what's known as a virtual image, an image that cannot be projected onto a screen. The opposite of that would be a mirror that curves inward, called a concave mirror. Concave mirrors tend to cause light rays to come together. As you can see, the light rays are converging, coming together. And typically, if you're really close to the mirror, like if you're between that dot and the mirror, it makes the image appear smaller, such as in this makeup mirror. But if you're on the outside of that letter F, the focal point, it will make things look upside down or inverted. So here's kind of an idea of what that means. So because the woman is far away from the mirror, her image is going to appear inverted or upside down, and that's what we call a real image, because the light rays actually, as you can see, do kind of cross paths and converge. Whereas over here, when you're close to that mirror, the image will appear enlarged, but it will be right side up, and that is a virtual image. And here we have a few definitions. Mirrors refract, lenses refract. Mirrors reflect, lenses refract. One more time. Mirrors reflect, what? Lenses refract, yeah. The thicker the lens is either in the middle or near the edges, the more refraction that takes place. So just as there are two types of mirrors, there are also two types of lenses. Some examples of where you might see a converging lens would be in a magnifying glass or possibly a camera. Places where you might see a diverging lens would be in someone's eyeglasses that's nearsighted. Typically the diverging lens is not used nearly as frequently as converging lenses. Converging lenses would also be in things like binoculars and telescopes and things of that nature as well. But notice what a converging lens does to light. A convex lens brings them together. Diverging spreads them out. When it comes to lenses and mirrors, there are two terms that you'll hear frequently. Something called the focal point and another thing called the focal length. So in this diagram here, this little small f is the focal point, and the distance from this f to the center of the lens would be the focal length. And here we have the the object. We have this big tall arrow, and then over here is the image that's produced when those light rays go through the lens. So we have two formulas, and I'll give you a chance to write these things down. So don't let the formulas scare you. I know they look pretty complicated, but we're definitely going to take your time. We'll help you work through it and help you understand what's going on. One word of caution, the little f looks a little bit like the f that we use for frequency, but we will always use, whenever you see this formula, just know that that is not a frequency, that is a focal length. Okay? So let's kind of look and see how we use these formulas. So here's an example of a light bulb, and there's a lens and the light is shining through the lens to the screen on the other side. Alright, so here we have the same image that we were looking at on the previous screen, the light bulb and the screen. So we're going to show how it works here. So we're going to use our formula of 1 over the focal length is equal to 1 over the distance of the image plus 1 over the distance of the object. Alright, so let's look and see how that works out. Here is our image over on this side. And so the distance is 1.5 meters. And then our object is 0.75 meters away. Okay, so we can't really add those together because they're different numbers in the numerator, but what we can do is find a common denominator, and most of the work that we're going to be doing in here, we'll try to make it pretty easy on you guys. So a common denominator for them would be 1.5, and so we'll add that together, and you get 3 over 1.5. So let's just kind of summarize it a little bit back here. So 1 over the focal length will be equal to 3 over 1.5. So what would we do here? If you cross multiply, 1.5 times 1 is equal to 3 times the focal length. Then we could divide both sides by 3. So the focal length ends up being, 0.5. 3 divided, and that's exactly what they have right here when we're done. So that's how that focal length formula works. It's not too bad, something we can easily do when we practice it a little bit more. The next formula we had was to look at the magnification. Well, you can already look at the picture and see that the image is larger than the actual object, but we're going to actually calculate that. And one way to calculate that is to take the distance of the image and divide it by the distance of the object. Now there's a negative sign in front of it, and so we'll talk about that in just a second. So we take that distance of the image, which was 1.5, and we divide it by the distance of the object, which was 0.75, and we get 2. So what we see here is that this image is twice as big as the actual object. So that's how we can figure out how magnifying that lens is. The fact that it's negative just means that it's inverted and upside down. So when you look at the eye is basically a nice little refraction area. The first part of the eye is this little part right here called the cornea. The cornea is that flap of skin on the outside that starts to refract some of the light that comes in. Then the next thing that is encountered is this opening, which is right here, is the pupil. And it's really just nothing more than an opening. And then you get to this thing, which is the lens. Now the pupil can get smaller and larger, and that controls how much light comes in. The lens can get stretched or squashed, and that helps to focus the image on the back of the eye. And the back of the eye is called the retina. It's kind of like the canvas or the LCD screen of your eye. So you can see here is the actual object, and the light reflects off of that object, and it goes through the cornea, through the pupil, through the lens, and all of that refraction takes place. And the next thing you know is the image is on the retina and it's upside down. And then that image is then sent to the brain for our interpretation. So you can see the focal point is right here on the retina. That's where, if you have normal vision, the focal point is on the retina. The focal length would be from the front of the eye, because that's where a lot of refraction is taking place, to the back of the eye. That would be the focal length. Now, some of us aren't as fortunate as others. Some of us are nearsighted, and if you're nearsighted, that means that your lens and your cornea refract too quickly. And so instead of this part right here being on the retina, it's right in front of it. So you need a diverging lens. If you're farsighted, here you are up here, then the image gets focused behind the retina. So here's the arrow right there, and you want it to be on the retina. So you need a converging lens. So the lenses that we spoke of earlier will help correct some of these vision issues.